Previously, when we wanted to find the variation of shear and moment, we had to either use an equilibrium approach or we used an integral differential calculus type of approach. And in less time than it's going to take to explain any of that, perform any of that, explain this, a new approach, we could have it just simply done. And it all hinges upon understanding what it means that the rate of change of something is equal to something else. So dV dx, the rate of change of the shear, is equal to the intensity of the distributed load. Well, there is no distributed load. It's equal to 0 in this case. So the slope of the shear function is going to be 0. Right, now what you're going to hear me say is the slope of the shear diagram is going to be 0 because we're going to plot this. This is a sort of pseudo-graphical kind of approach. We know from the last time we saw this problem that this concentrated force of 30 kips created a discontinuity in the shear of exactly 30 kips, in this case taking it downwards. Whereas this concentrated force will do the opposite. We'll start off at 0 and it will shoot us up in a discontinuity of the shear by exactly 7.5 kips. We have 0 slope, dV dx equals W, so no slope, goes over where the concentrated force is. Concentrated force sends us down by a delta of negative 30. Follow the direction of the arrow, so 7.5 minus 30 is minus 22.5. Again, we have no distributed load, so 0 slope. Bam. Come over to here, we're still at minus 22.5, and then the concentrated force closes us off. It is that simple and that easy to get this, right? Now with the moment, we hinge upon the same kind of thing here. Slope of the moment diagram is given to us by the value of the shear. We start off at 0 moment at this pin support on the edge, and then we got a positive support, or positive shear, right? And so remember we said that really shear had units of foot kip per foot. Well, it has a slope here, a 7.5 kip foot per foot. If we take then define the change in moment from one point to the next, we could integrate, but integration just means area. And that's a positive area that I've just hashed in at 7.5 times 15, or 112.5. So it shoots off at a positive slope because the shear is positive. We end up at 112.5, and then note over here we have then a minus 22.5 times 5, which is a negative 112.5. So we're going to come down at a slope of 22.5 kip feet per foot and end up at 0 again. Right? Wow. What you're not used to doing is drawing a function and then drawing the derivative of that function. You're used to maybe evaluating it at various places. You're used to going from here to here, and you're not used to doing it the other way around and drawing what it looks like. But it is this simple and easy, and we'll continue to show that in the next examples as we move along.